This is John Whitaker for the Probability 1 class, and this is our 17th video lecture, and this will be our last video lecture covering Chapter 2 topics. The last thing that we've been doing is that we've been talking about limit theorems, and we had done the strong law of large numbers last time, and this time we're going to do probably the most famous theorem along with the strong law of large numbers in terms of probability theory, and that's called the central limit theorem. But before we get to that, we're going to have to define a certain type of convergence which pertains to the central limit theorem. So here's the definition. A sequence of random variables x1, x2, and so forth converges in distribution to x if the limit as n goes to infinity of f, big F sub x sub n of a converges or equals to big F sub x of a for all 8 elements of R, where F sub x sub n of a is the CDF of x sub n, and big F sub x of a is the CDF of x. So that's what we mean by convergence and distribution for some random variables. And we have a fact. It turns out that this is the weakest type of distribution. Convergence. So as a fact, here I'll say that pointwise convergence implies almost sure convergence, which implies convergence in probability, which implies convergence in distribution. Okay, now I'm ready to write down the central limit theorem, and here's what it says. So the central limit theorem, what it says is that we start off with x1, x2, going on forever, be a sequence of independent and identically distributed random variables each having mean, that's its expected value, equal to mu, and variance equal to sigma squared. Then the distribution of this quantity. So it's x of 1 plus x of 2 plus all the way up to x of n minus n times the expected value all over the square root of n times sigma tends to the distribution of the standard normal random variable as n goes to infinity. We can write down a little bit more of what that means. What that means is, that is, for any real number a, the limit as n goes to infinity of p of x1 plus x2 plus xn minus n times mu all over the square root of n times sigma. The probability that this is less than or equal to a, that equals or goes to 1 over the square root of 2 pi times the interval from minus infinity to a of e to the minus z squared over 2 dz. Okay? And to prove the central limit theorem, we're going to take for granted a particular fact, a lemma, that I'm going to write down next. So let me write that down. We will prove the central limit theorem by using the following lemma. We won't prove the lemma. So the lemma is, if we let z sub 1, z sub 2, and so forth be a sequence of independent and identically distributed random variables, each having I'm sorry, I didn't write this down correctly. So the lemma says let z sub 1, z sub 2, this be a sequence. I'm sorry. Of random variables. I'm sorry. whose CDFs are, well, they'd be f sub z sub, let's say, n, okay, and moment generating functions phi sub z sub n of t, and I'll write this down. Okay, and let z be a random variable with CDF f sub z of t and moment generating function phi sub z of t. Then, if phi sub z n's of t converge to phi sub z of t, phi. Then the CDF, so the moment generating functions converge, then the CDFs converge to the CDF of f sub z, and that's true for all t for which f sub z of t is continuous. Okay. So we're ready to use that lemma to prove the central limit theorem. And the proof of the central limit theorem, as you'll see, is heavily reliant on some calculus techniques, particularly L'Hopital's rule. Okay, so here's the proof of the central limit. Okay, we're going to start off by, we'll let x sub 1, x sub 2, yada, 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 forever, be a sequence of independent and identically distributed random variables each having mean, so these are finite, mean expected value of x sub I equal to mu, and variance infinite equals to sigma squared. Okay. So we're going to break this up into cases. Okay. So the first case, as we've seen before, we've done before, is if mu equals to 0 and sigma squared equals to 1. Okay. Now, we're going to use that lemma about the moment generating functions converging That will force the CDFs to converge. And so what we'll start off with is examining the moment generating function. For this case, we're talking about for, first of all, x sub I over the square root of n, just that guy. And what is it? Well, it's going to be phi sub x sub I over the square root of n of t, and it's equal to the expected value of e of t times xi over the square root of n. That's what we have. So, the moment generating function for, if we would, the sum as I runs from 1 to n of this x sub I over the square root of n is, well, it's going to be equal to phi of this sum of the x sub i's over the square root of n. Again, I'm not going to write it, but I runs from 1 to n. Of t, which will be equal to the expected value of e times raised to the t times this sum. So I runs from 1 to n of x sub I over the square root of n. Okay? And so I'm going to expand that. And that's equal to the expected value, of, this will be e times t times x sub 1 over the square root of n, and it'd be plus t times x sub 2 over the square root of n, plus, we keep going, up to t times x sub n over the square root of n. And that's the same thing as the expected value of of tx sub 1 over the square root of n times e times t x sub 2 over the square root of n times so forth times e to the t times x sub n over the square root of n. Okay, just using laws of exponents. And due to independence, this is going to be equal to the expected value of e sub t of x sub 1 over the square root of n times the expected value of e sub t of x sub 2 over the square root of n, and so forth, all the way up to the expected value of e sub t times x sub n of the square root of n. Now it turns out that each one of these values are going to be the same thing because they are identically distributed. And so here's what I'll write. I'll say this is phi sub x. Well, here's the way that it can be thought of. You could think of this as phi sub x sub 1 of t over the square root of n. So here we're thinking of this phi being evaluated not at t, but but t over the square root of n. What would that be? It would be e of t over the square root of n times x sub 1. But that's exactly what we have. But here, this is going to be the same thing, except I'm going to have phi sub x sub 2. But they're the same thing as each other. These moment generating functions are because of the identically distributed nature of these random variables. So it's this guy, and how many of them do I have? I have n. Okay. So what we want to do is we want to show, in this case, that the phi sub x sub 1, if you will, of t over the square root of n, we want to show that guy, really I'll write down the limit as n goes to infinity, that converges
to the standard normal. And so what was that? That was e to the t squared over 2, the moment generating function for the standard normal. That's what we want to show. And I made a mistake here. It should be this quantity raised to the nth power. Okay, that's what we want to show. So we're going to be looking at this limit. Okay. So let's note that the limit as n goes to infinity of phi sub x1 of t over the square root of n raised to the nth power. What it goes to, okay, so as n gets really, really big, square root of n is really, really big. For any fixed t over really, really huge positive numbers goes to 0. The moment generating function evaluated at 0, well, that would be really the expected value of x raised to the 0. That's by one of the properties we have about the moment generating function. Okay, and so what is the expected value of x to the 0? Well, x to the 0 is 1, and the expected value of something that's always 1 is 1. So this quantity that's being raised to the nth power is 1, and then n is going to infinity, so it's 1 to the infinity type of limit form. That's an indeterminate limit form. We don't know what that is. And so we have to do work to compute this. So what we do is we consider, instead of this limit of this function, we consider the limit as n goes to infinity of ln of this function. Okay? And that isn't going to be the answer to the problem we're looking for, but we can use that answer to get to the answer that we want. Essentially, whatever answer we get here, we're going to raise e to it. The e raised to that answer will be the limit of what we're looking for. Okay. Well, this is equal to the limit as n goes to infinity. Here, before I go any further, let me back up. This is going to by properties of logarithms, I can pull down this n. And then I have ln of phi of sub x of 1 of t over the square root of n. And what is this going towards? Well, n is going towards infinity. As n gets really, really huge, this goes towards 0. Phi of 0 is going towards 1. Ln of something going towards 1 is going towards 0. That's an indeterminate limit form as well. So how we handle that is we'll rewrite this as the limit as n goes to infinity of ln of phi sub x of 1 of t over the square root of n all over, well, 1 over n. 1 over n down here, pull the n up there, so it's n to the minus 1, that's where I write it. And then this is equal to 0 over 0. Now that's an indeterminate limit form which L'Hopital's rule would apply. So that's what we're going to do. Okay. All right, so this is equal to a limit, so I'm applying L'Hopital's rule, as n goes to infinity. Now, ln of something, its derivative, is 1 over the something, so that's going to be phi sub x of 1 of t over the square root of n, times the derivative of what we were taking ln of. So that's going to be phi prime sub x of 1 of t over the square root of n. And using the chain rule, we're going to have to take the derivative of t over the square root of n. Now remember, we're taking the derivative with respect to n. And so this is going to be equal to, so really rewriting this as an advantageous form. It's t times n to the minus 1/2. So we have this derivative, minus 1/2 t n to the minus 3/2 all over, and the derivative of n to the minus 1 using the power rule would be minus 1 n to the minus 2. Okay, we can simplify that a little bit. That's equal to the limit as n goes to infinity. Here this would be phi sub x sub 1 prime of t over the square root of n. The minus 1/2 and the minus 1, that's going to make a positive. I'm going to put a 2 in the bottom. There's a t here. The n to the minus 3/2, I can pull down here to be an n to the positive 3/1/2. So that leaves n to the minus 1/2, minus 2 plus 3/2. And then we also have this phi sub x sub 1 of t over the square root of n. Okay, now when I look at this, before we go any further, as n goes to infinity, this goes to 1. Phi prime evaluated when n goes to infinity, this goes to 0. Phi prime evaluated at 0 is nothing more than the expected value of x sub 1. But we're assuming in this case that the expected value is equal to 0. So the top is going to 0. What about the bottom? Well, here, remember, this t over square root of n is going towards 0. Phi of 0 is equal to 1. But 1 over n to the 1/2 power as n goes to infinity goes to 0. This is 0 times something going to 1. That's 0. So again, I'm going to have to use L'Hopital's rule. Okay. So I take the derivative of the top. Okay, so I'm taking the derivative with respect to n. So this would be phi double prime sub x sub 1 of t over the square root of n. T is a constant, I just write it down. Then I have to take, by the chain rule, the derivative here. So that's going to be minus 1/2 t to the n to the minus 3/2 all over. Okay, now this bottom, when we take its derivative, let me write this limit a little bigger. Okay, so I might use the product rule. So I'm going to write down first 2, I'm going to take out a 2. Okay, so n to the minus 1/2, and then I take the derivative here. This is going to be phi sub x1 prime of t over the square root of n. The derivative of this guy is going to be t times minus 1/2, so I'll write down minus 1/2 t times n to the minus 3/2. Plus, using the product rule, I'm going to write down the second, which is phi sub x sub 1 t over the square root of n, and then the derivative of n to the minus 1 is going to be minus 1/2, I'm running out of room here, it's minus 1/2 n to the minus 3/2. Not visible. I think it's visible. What we have in each one of the terms is a minus 1/2 of n to the minus 3/2. It's here, and it's here. And so I'm going to cancel that out. When I cancel that out, what I'm left with, if this is equal to the limit as n goes to infinity, it would be phi sub x sub 1 double prime of t over the square root of n. I had a t previously, and another t is going to exist, so that's t squared. Aha, that's important. Remember that t squared was involved in the moment generating function for the standard norm. Okay. In the bottom, we got this 2. And here, we would have n to the minus 1/2. There's a phi sub x sub 1 prime, okay, of t over the square root of n. Okay. And then there is a t to multiply that by. And then there's plus phi sub x sub 1 of t over the square root of n. And that's all that's there. Now, when we look at this, as n goes to infinity, right here, this is going to be the expected value of x squared. Now, let me just make this comment. Since, in this case, the variance, well, this is 1, sigma squared equals 1 in our case, which equals to the variance of x sub 1, which equals to the expected value of x sub 1 squared minus the expected value of x sub 1 to b squared. And the expected value in this case of x sub 1 was 0. Then we have that expected value of x sub 1 squared has to be equal to 1, which is the same thing as phi sub x sub 1 evaluated at 0. And so as n goes to infinity, this goes to 0. This is the expected value of x squared. So that's 1 times t squared. And in the bottom, this guy's going towards 0. This is going towards 0. Phi prime of 0 is expected value of x sub 1, which would be 0. So 0 times 0, that's 0. 2 times 0. Plus, or times t, so that's still 0. Here, this is going to be going towards 0 here as n gets really big. Phi of 0 is equal to 1. And so we end up getting t squared over 2. Okay, that wasn't the original limit we were trying to get, but it helps us get the original limit. Okay. So, the limit as n goes to infinity of t, this is what we're trying to answer, of x sub 1 of t over the square root of n, all that raised to the n. Well, we had found ln, the limit of ln of that. So to undo taking ln, we would raise e to the answer for the limit of the ln, and that's t over 2. Ha! So in this case, okay, so by our lemma, okay, we have the CDF of x sub 1 plus x sub 2 plus x sub n all over the square root of n converges to the CDF of the standard normal. And that proves the theorem in this case. What was this case? This case was where the mean was 0 and the standard deviation, and the variance was 1. Okay, so we have our second case. That is, the mean is something different than 0, or the standard deviation is something different from 1. So in this case, what we do, consider x sub I stars equal to x sub I minus mu over sigma. Then what I want to tell you is that the x sub I stars will be independent and identically distributed we look at the expected value of x sub I minus mu, I should write it down this way, x sub I star, which equals to the expected value of x sub I minus mu over sigma. Okay, so here, this is equal to the expected value of x sub I, well, you pull out the 1 over sigma. This is x sub I minus mu, and so that's equal to 1 over sigma times the expected value of x sub I minus the expected value of mu. But the expected value of mu is just mu, and the expected value of x sub I, that's mu, so this is 1 over sigma times mu minus mu, which equals to 0. Okay, and also notice that the variance of x sub I star, that's going to be equal to the variance, of x sub I minus mu over sigma, and what that's equal to is the expected value of x sub I minus mu over sigma to be squared, our formula, minus the expected value of x sub I minus mu over sigma, that quantity to be squared. This second part we know to be equal to 0, we just calculated it, and so this is equal to 1 over sigma squared, when I square it and pull it outside of the expected value, and then times the expected value of x sub I minus mu to be squared. Now, if you remember that mu is nothing more than the expected value of x sub I, and if you remember the definition of the variance of x sub I, not the formula that we used here, but the definition of the variance of x sub I would be the expected value of x sub I minus the expected value of x sub I. That's to be squared. That's exactly what we have here. So this is 1 over sigma squared times the variance of x sub I, which we're assuming to be sigma squared, so that's equal to 1. So, by our first case, the x sub I stars fall into the first case. We have that the CDF of CDF of this x of 1 star plus x of 2 star plus all the way up to x of n star over the square root of n converges to the CDF of the standard norm. Here's what we do. We know that x of 1 star plus x of 2 star plus x of n star over the square root of n is really equal to, by the definition of these x of I stars, it's x of 1 star, x of 1 minus mu over sigma plus, this will be x of 2 minus mu over sigma, plus, we'll continue on, so it's x of n minus mu over sigma, all over the square root of n, which is equal to x of 1 plus x of 2 plus all the way up to adding up to x of n, minus n times mu. Okay, the sigmas will be in the bottom times the square root of n. So the CDF of this guy, which is the same thing as the CDF of what's written here, converges to the standard normal. And that is the proof of the central limit theorem. Okay, I would like to do an example of where we use the central limit theorem. So as an example, if 10 fair die are rolled, find the approximate probability that the sum obtained, so the sum of the 10 dice rolled, is between 30 and 40. So here's our solution. Here's the solution. Well, what we're going to do is we're going to start off by letting xi denote the ith row. The ith die. Okay? Row or outcome. Okay. Now, here's the thing to notice. You know, what happens on one of the dies that we're rolling, it's not going to influence what happens on the other one. So they're independent, okay? And they're identically distributed. So here, if we notice what the expected value of any one of the x sub i's would be, they're all going to be the same. Well, because this is a discrete random variable, we can just make one die roll here. And what the answer would be the sum of the output values. Well, the output values would run from 1 to 6 of x sub I, f of x sub I, where f of x sub I is the probability of getting that die roll. Well, getting any one of the die rolls, is the chance of that happening is 1 out of 6. So this is equal to 1 times 1 out of 6, plus 2 times 1 out of 6, plus 3 times 1 out of 6, plus 4 times 1 out of 6, plus 5 times 1 out of 6, plus 6 times 1 out of 6. And what that's equal to, let's see. So there's 11, 15, 18, 20, 21 out of 6. Okay, and that's the same thing, 21 out of 6. What is that? 3 goes into both. So that's 7 halves. 7 halves. Okay? That's what the expected value of an x sub I is. They're all identically distributed. Their means all the same. 7 halves for each of the diagrams. Okay. Now, the variance of an x sub I, okay, it's going to be the same for all the 10 dice, so 1 through 10 here. Well, that's equal to the expected value of x sub I to b squared minus the expected value of x sub I squared. Okay. Note the expected value of x sub I squared, well, that's going to be the sum over the x sub I values, which are 1 through 6. That's the die roll outcomes that are possible. Of x sub I squared times f of x sub I. Let's see, that's equal to, this would be 1 squared plus, times f of 1, which is 1/6, plus 2 squared times 1/6 f of 2, plus 3 squared times 1/6, plus 4 squared times 1/6, plus 5 squared times 1/6, plus 6 squared times 1/6. And so this is equal to, let's see, 36 and 25, I think that's 41, I think that's 61. 61 and 16 is 76, 85, 89, I got 90. Let me try again. That's not right. So 36 and 25, that is 61. 61, this is plus 16, I think it's 77. 86, 91, that's right. So it's 91 over 6. Okay, that's what we get. So, that's the correct answer. So the variance of x sub I is equal to 91 over 6 minus, here this would be 7/2 to b squared. So we get 91 over 6 minus 49 over 4. Common denominator is 12, so this is 182 over 12 minus 3 times 49, I think that is 147 over 12, and here this becomes 35 over 12. That's the right answer. Okay, so what do we ask to find? So we will approximate the probability. This was our problem. If 30 is less than x of 1 plus x of 2 all the way up to plus x of n, which is less than 40. Okay? Using, I'm going to write this a little bit. Using the probability that, let's say 29.5, so this is just an approximate, less than or equal to x of 1 plus x of 2 plus x of n is less than, let's say 40.5, less than or equal to. Okay. And so here, we're not in perfect position to use the central limit theorem, but we can put ourselves in position to use the central limit. What I need to use the central limit theorem is a sum here of independent and identically distributed random variables minus n times mu. So mu here, what was that? I think that was 7/2. And so 7/2 times n. You know, I should have written n. We know what n is. N is 10. Okay, so 10. So here, I want to take away 10 times 7/2. That's 35. So I'm going to take away 35 from all parts. So this probability is 29.5 minus 35 is less than or equal to x of 1 plus x of 2 plus x of 10. So now I got it. Minus, this is 35, which will be less than or equal to 40.5 minus 35. This is the same thing. This is probability, what is this? This is minus 5.5. Less than x of 1 plus x of 2 plus x of 10 minus 35, which is less than or equal to, this is 5.5. Okay? This is still not perfect position for the central limit theorem. We need to have this divided by the square root of n times sigma, or the square root of n sigma, sigma squared underneath the square root. Okay? So I'll do that. What do I need to divide by? Well, let me write it here on this side. So that's equal to the probability. Okay. So here in the middle, I have x of 1 plus x of 2 plus x of 10 minus 35. What I want to divide that by is the square root of n, which is 10. And then it should be sigma, but I'll make it sigma squared underneath. And sigma squared was 35 over 12. And so I better divide all parts by that. So this is 5.5 divided by square root of 10 over 35 over 12. Here, less than or equal to minus 5.5 over square root of 10 times 35 over 12. Okay, this is the same thing as the probability of approximate, okay, let's do some rounding here, of minus 1.0184 less than or equal to this quantity in the middle. Less than or equal to 1.0184. Okay? And so this is like the standard normal. So what this is going to be approximated by is the probability of, here I'm going to rewrite this as minus 1.02, is less than or equal to z, the standard normal random variable, which is less than or equal to 1.02. That's the way I'm going to truncate or approximate that decimal. Okay, this is the standard normal. We're almost done. Okay, so how do we compute that probability? Well, we'd have to integrate the standard normal's PDF over that region. And really, we could say, in terms of symbols, what the CDF, I'm sorry, the PDF of the standard normal is that 1 over the square root of 2 pi, and then it's that e to the minus z squared over 2. As a function, what it looks like is this bell-shaped curve. Okay? And so what we're looking for is we want to integrate that from minus 1.02 to positive 1.02. And what that does, that integral, it represents this area under this curve. That's what we're looking for. Okay? Well, it turns out that there are charts. And this integration of that function, its PDF, it doesn't have a closed form. And so we have charts or computers or calculators that helps us approximate this. And one of the charts that we have in the book would say, well, if you look at this, this is what we're looking for, this area. This will be equal to this area. It's this area that I'm drawing here, going on forever, back this way, minus this area. This region taken away. So the region to the left of 1.2. So you, minus 1.2. So you take the area to the left underneath this curve from 1.02 and subtract from it the region that is the area to the left of minus 1.02 underneath this curve. Okay? That gives you this region. But this would be phi, if you will, sub z of 1.02 minus, this would be phi sub z, the standard normal CDF. Okay, that's what I mean by this. Let's write it as big F. Of minus 1.02. And I said we had charts that have calculated things like this. And our book has a chart that calculates the CDFs of these numbers, but it doesn't have it for negative ones. So I'm going to say this is the same thing as phi sub z of 1.02. Now, how do I represent this? Well, here's what I can say. This area over here, because of the symmetry of our PDF, well, I didn't draw it very symmetric that time. All right, let's say it's symmetric. So this area is really the same thing as this area to the right. So how would I describe that? Well, give it a few more minutes. We're almost done. That's equal to phi sub z of 1.02 minus, well, the way I can rewrite this is I could say, hey, look, this picture that we have, right here, the picture that we want, this area, this region right here, one to the right of 1.02. Really, that can be thought of as the whole, that's equal to the area under the whole curve, all of it, okay, minus the area to the right of 1.02. And so the area of this whole curve is 1, because that's what the PDF gives us if you integrate. It gives us 1. Minus this area here is nothing more than the CDF of the standard normal evaluated 1.02. And so what we end up getting is phi sub z of 1.02, well, twice, minus 1. And this is something that's approximated in the chart that's in our book. And let me tell you what that numerical value is. This is equal to 2 times 0.8461, so it's from a chart, minus 1, and that's equal to approximately, let's say equal to 0.6922, and that's our approximate answer. All right, ladies and gentlemen, we're going to call it quits with that. Thank you very much for your attention.